Right, so welcome back. Today I'm going to be talking about design Discord. So this is a fun system design problem involving designing uh, a chat service with that can support lots and lots of users in a specific group. So that's kind of the key differentiating factor between Discord and a service like a WhatsApp group or something like that, where we need to support, we can have thousands of members per group and per channel, per server and per channel. Um, so the first thing that I want to do, I want to talk about some key requirements here. So the first requirement is that users can uh, join servers. So users can join servers. Servers have multiple channels, so server users can join servers slash channels. Um, then users can send and receive messages to channels. Okay, and then so users can join servers and channels. Users can send and receive messages to channels. And then what other requirements do we want to support? Um, Users can send and receive messages to channels. Um, let's do users can see who else is online. This is a good one. And let's do scale. 100 million daily active users. Let's say 10, let's say 50 messages per day. And let's say 100. Let's say, okay, 10 messages per day sent and 100 received per user. Some could be more, could be less. And then the other key consideration for scale is that we want to support high volume channels. So this is a key thing. High volume channels, 10,000 users per server. Sorry, high volume servers, 10K users per server. So we have a lot of messages going back and forth and on a one particular server. So we have 1,000 messages received per user. So we're basically sending and receiving lots of messages, and we have lots of messages, well, we have lots of users on a particular server. So that's very important. So the non-functional requirements. So our first one we want to think about in terms of CAP theorem. I like to start with this one because it's a good opener to discuss other non-functional requirements. So here, I think that we want to prioritize availability, and we want like a 99.99% availability over consistency. Here's the thing is multiple users are going to be sending messages to each other and all that kind of stuff. So um, the thing is like it will take we want to make sure that the users eventually get their messages, but messages are unique per user. We just want to make sure that the user who's receiving the message eventually gets that message. We don't need to we don't have like a contention between a message where only one needs to exist. So that is a key thing, and then we can just say here we'll just explicitly call out that we're going to be using eventual consistency. So this is our CAP theorem, latency. Um, we want messages to be near real time. So you want like a 200, like a less than 200 millisecond delay between send and receive. Scale. Yeah, so the important thing for scale here is that we have high volume servers with lots of fan out. So an interesting problem that we need to consider here is how do we enforce this near real-time delivery of messages? How do we handle all of this fan out? And uh, how do we support 10,000 users per server? So that's going to be an interesting question there. Scale. Um, what else? So we do need to consider fault tolerance, durability. We want to make sure that no messages get lost. So every time a message is received, everybody who's supposed to receive it does in fact receive it. We also want to make sure that if a part of the system goes down, we have a mechanism for retrying anything that might be um, that might be impacted, maybe with just like a slight delay or something like that. So these are pretty good functional requirements. And then I'm going to move on to our core entities of the system. So we have a user, we have a message, and we have and I think I'm actually going to just alter this slightly. I'm going to remove this requirement for now because I just want to laser focus in on this supporting the 10,000 users per server requirement and the other things that we do. And then I'm going to put, so out of scope is going to be what we talked about, which is seeing if users are, are online. And I'm also going to remove seeing if users are online and sending me media, and then privacy, GDPR. Um, so these are important considerations in a real system, but I'm going to put them out of scope for this system design interview question. So core entities, user, message, server, and channel. So in Discord parlance, a server is a group of users, and then a channel is one particular topic of messages within that server. Typically, users are consuming messages from multiple channels per server, just to get aligned on sort of our terminology there. Um, so API routes, we're actually going to be using WebSockets for this. So we're doing frequent bidirectional communication between the server and the client, which means that we need a WebSockets interface. So first, we're going to talk about some of the messages that the client sends the server. So we want create server. This is something that we do infrequently, but we might have more frequently, we'll have join server, server ID, and then join channel, channel ID. And then the client send message, channel ID, message. So those are some things that the user can do to the server. Server to the client. So these are messages that are passed from the client to this to the or from the server to the client. So notify. Uh, so send a new message, channel ID, message. Oh, and then also we should have like get messages, channel ID, and then a cursor. This is going to return like paginated messages, something like that. We have a way of basically, if the user's been offline, we can we need to know like we need to be able to access all of the messages that are on the server, and so we need a mechanism for doing that. So we're going to fetch that. We'll pass in a cursor and say, basically, this is the last message I have. Give me all the messages since then, and then the client will connect to the server and download all those messages. So server connects to the client, new message. So this is basically the server notifying the client that the user that there's a new message on a particular channel, and this is the content of the message. What else? So users can join servers and channels. Users can send receive messages to channels. And then we probably have like notify, status change, channel ID, and then user ID. So if a user joins or leaves the channel, although this is not a functional requirement, so I'm actually going to remove that and just stick to our core functional requirements. I think this covers our core functional requirements. So we can move on to the high level design. So first of all, we're going to have a, oops, client. And we're going to be using WebSockets here. So I'm going to have a service here. So we're going to have our chat service. I'm going to keep this really simple to start, just our main requirements, and let's just forget about scaling for a second, even though we know that this isn't going to scale, and we're just going to have the client connect to a single instance of chat service. We're going to open a WebSockets connection. We just have one box here for now. Obviously, this doesn't scale. I'm going to come back to this in a second. Then we have our database here, and we are going to uh, basically, so users can join servers and channels. So we have a server here. We have an ID, title, description, dot, dot, dot. Then we have a channel, ID, title, description. And then we have here server ID. Cool. So the client first opens a WebSockets connection with our single instance of chat service. They're going to call create server. We probably want like a title and description. This tool is called Excalidraw. This is very commonly used for system design interviews. Um, so highly recommend getting familiar with this particular tool. It's totally free and it does collaborative editing. So good thing to learn. We have a server and we have a channel. So these are our database records. So the user is going to call create server, and then they'll also probably need an API to create channel title, uh, server title description. So I forgot that in my APIs, but that's creating a channel. So then we can chat service will then talk to the database and create the server and the channel. And then we probably have also something like this. We have our users. We need the users need to be able to join servers. So we have our user ID, we have their name, we have their email, whatever. um, etc. And then we have server member, or we'll just have member. Server ID and uh, user ID. So now we can support the other requirement, which is users can join servers and channels. So users can join servers. So client opens a WebSockets connection with chat service. They say, I want to join this particular, I want to join this particular server. Um, and I think that they're automatically joined if I with Discord, they're automatically joined for every channel within the server. And so we're just going to have them join the server. And so they'll just join the server. So they'll open a WebSockets connection with chat service, and then chat service will basically go ahead and say, I want this particular user to be associated with this particular server. So we will create a record in our members table that says this user is now on this particular server ID, and they will essentially subscribe to any messages that come in for any channels within that server. So they're connected to this, they're connected to the server, they have a record in the database now. So users can send and receive messages to channels. So this is our next one. So we have a send message channel ID. So we probably also need the server ID here. Now maybe channel ID is enough because channel ID implies a server ID. So get send message channel ID message and get messages channel ID cursor of messages. So what we need here, so the client opens WebSockets connection with chat service. Chat service will then need to send a message. So it's going to need to append a message to the database for a particular channel. So we have our channels here. The channel has an ID, it has a server ID, and then it has a title and description. So what we need here is we need a message of a channel ID, user ID, message, timestamp. This is like a really good thing to have for like a created date for each one of these. But I'm going to say it's kind of implied. So we have our message here. So in our chat service, when the user sends a message, they will send us the message associated with this to a particular channel. So the channel ID. So first we need the server ID. This is important. So if we get the message and we only have the channel ID, we need to go, and for this channel ID, we need to look up the server ID. So we have the server ID, and then for our message, we will have the server ID and the channel ID. Maybe we'll just have this be a part of this, but we essentially still need to validate that the server and channel are valid before we actually write the message. So we'll basically do some validation within chat service on both of these fields to make sure that this is like a real server and channel that's coming in, that the message is valid and everything. And then we will essentially insert this message our into our messages table in our database for this particular user has written this message at this particular time. So now we need to focus on. So we figured out how to send messages. How do we actually get those messages to the other users? So right now we're in this very simple reductive design where we just have a single instance of chat service, and so we have all of these clients open with WebSockets connection with the chat service. And so what we can do is we just keep track of all of these other clients that are connected in memory. We have a durable copy of this message stored in our database, and then after we write this message to our database, we can just use those open WebSockets connection with an internal map. We have an internal map of client to, so we have user to WebSockets or WebSocket. And so what we can do is we can look up all of the members associated with this particular channel, or we can just cache this in memory as well. The users that are joined or not joined to a particular channel because we're still working on a single instance of chat service. So we basically know already which users are subscribed on which particular server. So we look up all of the users that are on a particular server and we say, hey, let's deliver this message immediately using WebSockets to all of those other users. And the API that will do that is we'll call new message. So we'll basically have a for loop and we'll go through all of these users. We'll look up their WebSockets connection from this map, and then we will call new message for each one of those users. So all of those users connected to the one instance of chat service will get that message. Moving on a little bit faster now. So for get messages, so the client will call get messages with a cursor. We can do a query on our database for all of the messages. So this is when the user was offline for a period of time and they're reconnecting to the server. And so they will basically call get messages for this channel ID. Maybe when they open that channel ID in Discord or whatever, we would just want to do a quick fetch of those messages. And so we can open a WebSockets connection with chat service, which will then go ahead and make a query for, they'll say, okay, uh, basically we have the cursor ID. We'll check first if the user is a member of this server and channel, and then if they are a member, we can collect all of the messages ordered by the timestamp for that particular user. Okay, so I'm going to go a little bit more quickly now. So let's talk about I want to talk about cap theorem a little bit later. Let's talk now about scale, because this is kind of the key thing that we need to drive into here. So we have high volume servers with lots of fan out. Obviously, this will not scale to multiple to many concurrent users. We have 100 million daily active users, and we have 10,000 users per server. So it's not possible even to host a single server on a single chat service instance. Maybe, but it would be pushing it. We should not design for that. We should definitely horizontally scale this chat service. So how could we actually do that? So now a client opens a WebSockets connection to a horizontally scaled chat service, which means that they are not necessarily on the same instance of chat service. We are now on multiple instances of chat service. What we need to do is we need to essentially find a way to deliver the messages between chat service instances. So the first thing that we're going to do, and this is sort of a beginning approach, it's pretty solid beginning approach, but we can talk about this more in depth. Is if we have multiple instances of chat service, we need some way of load balancing between them. So we're going to introduce a TCP load balancer here. So this is a layer 4 load balancer. Um, And essentially, this just acts as a pass-through to chat service. So it just will do a round robin approach and assign the WebSockets connection to one of these instances based on a simple strategy like least cons. And so we have essentially with a layer 4 load balancer, and this is the first of a couple strategies that we'll talk about here for how we could actually distribute the load in a smart way across all of these different chat services. So this is one approach. Could be solid, could be naive. We'll get to that in further detail. But this basically round robins to one of the chat services. And then each chat service also needs to know which user is connected to which WebSocket. We still need that map, but we don't necessarily have the users on the same instance of chat service. So we can't do this thing where we just write to the database and then notify all of the other users for that server. We need to be able to have the users that are connected to other instances of chat service be notified that there's a new message. So what I'm going to do in order to do that is I'm going to introduce Kafka here. And the reason I'm using Kafka is because we have a lot of volume of messages going through our system. We have 10,000 users per channel, so we have really high throughput requirements in that we need to process lots and lots of messages. We also have a requirement for message durability. So we want to make sure that no messages get lost. That's one of our key functional requirements. Kafka provides strong durability for messages, so we're guaranteeing that when a user sends a message, it's going to be stored in Kafka, and one way or another, we are going to process it. So The first thing that happens is when the user opens L4 load balancer connection to one of these instances of chat service, and then they will just write their message to Kafka. And we'll talk about how to deal with the database in a second. Then, so chat service is now a producer for Kafka. So chat service is going to produce messages which are inserted to Kafka in a topic per server. Topic per server. And then we have multiple channels per server. We can talk about this scalability considerations of why we're choosing server versus channel. So one consumer group. So let's talk first. So the first consumer that we need to talk about from Kafka is going to be our database. So we'll have some sort of um, we'll have uh, we'll have some sort of processor here, consumer here. Uh, Maybe it doesn't need to be called out specifically, but we have a consumer group that's basically pulling from Kafka and just sticking data into the database. So this is going to be like a Lambda. Um, and so once a message gets sent by a user, we are creating a persistent record in the database with the message that that user sent. So every time a user sends a message to one of our chat service instances, we write that message to Kafka. That eventually gets processed through. We have a Lambda here, which basically is just consuming messages from all of our Kafka topics and then inserting those messages into the server. So this gives us eventual consistency. We're ensuring that the messages for each particular server and channel eventually end up on the database. The next thing that we need to do is we need to actually make sure that the users are notified of those particular messages. So what we want to do is, let's say we have two users. User A is connected to chat service 1, and then user B is connected to chat service 2, and they're actually on the same server. Well, when user A sends a message to their server, they write via chat service that to that particular topic for that particular server. That message gets processed through Kafka, and then eventually we get to the end of Kafka, and then that message is consumed by chat service B, which is consuming all of the messages for that particular server, and then that message is eventually delivered to that particular client. And so this way, even though those clients are connected to different services, different instances of this service, we can still route messages between them. Now, this does add latency. So we probably have about 100 milliseconds of latency added by Kafka, but we're still within our 200 millisecond delay send and receive. So this is like 2 milliseconds because we're assuming that we're in the same data center here. This is 2 milliseconds. This is pretty lightweight. We're just bouncing messages back and forth between Kafka. And so this is pretty lightweight and managing the WebSockets connections. So chat service doesn't really do a lot of processing. Maybe we have 2 milliseconds here. And then, yeah, all of these hooks are within the same data center. So maybe we have 8 milliseconds here and 100 milliseconds for Kafka. So we're still well within our 200 milliseconds latency budget. We are limited a little bit by the client's connection to our data center. And so this is something to where we might want to consider like sort of localizing, geolocating our chat service instances a little bit closer. We can dig into that more in a second. But in terms of the parts of the system that we have more control over, we are good. And so the other thing is, if a client is disconnected, um, so another thing we need to do is we need to update this internal map. We need to track which Kafka topics uh, we're actually interested in following, right? So when a user connects to a chat service instance, they will say basically, I want to participate in this particular I want to participate in this particular server, and so the user then may say that I am interested in I have a particular WebSocket. and I have a particular set of servers that I'm interested in, servers. And then what we need to do is this chat service instance, or each instance, knows which servers are associated with each users. And then I might have like a map that server one, and then user two, user three, whatever. So I have two maps. One is from user to my WebSocket connection and which servers I'm interested in. And then maybe I have another map that's my server and then the users that are connected to that particular server. And then what I can do is when a user connects, I can say, hey, I actually have a user connected to this particular server. And so what I want to do is I want to establish I want to actually start consuming messages from this Kafka topic. We only need to consume messages from a particular Kafka topic for a particular server if there's a user connected to to that particular topic. So that's an interesting way of reducing the load that we actually need to process on our chat service by limiting it to the users that are connected to that particular topic. So that's an interesting thing there. Um, So let's talk a little bit more about this Kafka queue that's powering our messages. So we have a topic per server. The one thing to note is that Kafka does have kind of a limit on has a soft limit on topics. So it's not really designed to handle like hundreds of thousands of topics or anything like that. So we do need to. So this is why we're putting it on server. We're going to assume that most users are going to actually just be members of servers and not admins of servers. So it's possible that maybe we have some small servers where like maybe it's just one user with a group of friends or something like that. But we would expect that typically most users are just going to be joining servers that other users have created and not creating their own servers. So this is a kind of an assumption baked into the system. We may need to consider as the system grows in complexity, if we do find that we have like many uh, servers, we might need some way of grouping them into topics so that we manage the number of topics that Kafka is actually doing. So I'm actually going to use like a managed Kafka here, just so that we don't have to operationally manage our own fleet sizes or anything like that. Um, so partitioning, we probably also want to partition on server. So we have the topics and the partitions. That makes sense. Um, then we also want to consider replication. So we're going to have some replication. We'll have a certain number of other Kafka um, like broker instances acknowledging the rights to a particular topic. So we may configure this to say that like we'll have a replication factor of 3 or something like that. And that provides a pretty good durability on the messages to ensure our non-functional requirement of fault tolerance and durability there. So we have replication within the topic. So we have multiple partitions that are divided across multiple hosts within this Kafka cluster. And then those partitions have a replication factor of 3, which means that basically 3 different replicas of that partition have to acknowledge the rights so that we have good durability um, in case one of those partitions goes down. So Kafka is sort of known for its ability to handle lots and lots of messages going through. We have that high throughput requirement, but we also have that high durability, and we can store those messages store messages for days or something like that, 14 days. Um, So then chat service, the one thing that we didn't talk about was now we've disconnected chat service from our database, but we still have the use case where we need a client has been disconnected for a server from a server for a while. We need to fetch all of those new messages for that particular client. And so we need a query from chat service to the database to actually fetch those messages. Another thing chat service is going to do is like when a user sends a message, we do need to do some validation on that message. So we want to make sure like that channel and that server actually exists before we put the message in Kafka. We make sure that we don't put a lot of garbage into Kafka. So we'll do some surface validation. We will have chat service talk to this database for the fetch messages within a certain timestamp and all that kind of stuff. So we talked about one dimension of scale, which is basically this Kafka thing, how we handle lots of users connected to the same server. Another thing I want to talk about is our database choice and how that factors into our scalability requirements. So we do have 10 messages per day sent. So if we do some quick math here, we have 10 messages per day times 100 million daily active users. We have 1 billion messages per day. Messages sent per day. If we divide that by 100,000, then that means we have 10,000 messages sent per second. So 10,000 messages per second is a good amount of volume, but it's not a tremendous amount. Most databases can keep up with that sort of write throughput. Um, Kafka also can easily handle that sort of write throughput in terms of 10,000 messages per second. We could probably handle even more. We could handle hundreds of thousands of messages per second. So if we did want to scale up even further, we said 100, we have 10 billion messages per day. We have 100,000 messages per second. So then we start running into our more interesting conversations about what database we want to choose. And since we have such high write throughput, Kafka is a good choice here to manage that high write throughput. But we probably want to pick like an LSM tree database here. So we can pick like Skilla is a good choice, which is Cassandra, but a little bit more efficient. Dynamo is also a good choice, although we do have to be a little bit careful that DynamoDB we have a write provision write throughput, and if we exceed 40K on a brand new table, we do need to like reach out to AWS and give them a heads up that we are going to be passing a lot of messages, and we do need to consider our scaling considerations. We need to sort of fine tune that. Um, so that's an important thing. In terms of partitioning, I think generally we're keying everything off of our server ID. So this is going to be, I'm not going to go into too much detail here about partition key, but basically we are going to have server ID as our partition key for a lot of these different things. So for, yeah, I'm prepping like it's a real interview. Yeah. Um, so we have partition key for message, for server, for channel. Um, so users will be something different, probably user ID, and then member. We do want this to be the partition key. But the other thing is we will need to look up all of the servers that a particular user is a member of. So we want global secondary index on user. So this way we have an efficient query to see what servers the user is a member of, and also which server for a server ID we can query do like a range query on all of the different users that are a member of that server. So that gives us the different queries that we have here. Partition key. And then, yeah, so for message, we probably want this one to be our sort key. We probably want like a composite of the channel ID and the timestamp as our sort key there. We can dig into that further, but I want to talk about some other stuff before we sort of wrap up this design. So we talked about CAP theorem. We have eventually consistency for the messages. We're passing those through Kafka. It may take a little bit, but we are prioritizing availability. We're just writing to Kafka when we send a message. That's our only dependency, and so we are highly available. Um, We're not doing any sort of ACID or transactionality or anything like that. We're basically just passing those messages along. So messages to be delivered in near real time, 200 milliseconds. We've got that. We said the Kafka adds 100 milliseconds. We should tune this very carefully to make sure that we are optimizing for our latency. The other thing that we can do in order to optimize our latency further is that we can essentially bounce these messages. First, we have an internal map here on our chat service instance, which indicates which users are connected to which servers and which servers represent each users. And so if we want to really optimize our latency here, what we can do is we can actually just, when a user is, or when a client is connected to a particular chat service, we can say, oh, there's users that are already connected to this. We can just bounce those messages directly to those other users. And so what that does is that we can essentially um, uh, uh, skip the Kafka queue entirely for those messages that need to be sent to other users. It's still going to go on Kafka. The message always goes on Kafka, but we can essentially short circuit the message delivery so that we don't have to wait for that message to get all the way through Kafka before we deliver that message to the other user. And so it just happens if conveniently, if we have two users that are round robin to the same chat service, we can fast track that message so it goes from user two to user three, uh, in without ever leaving the box. So that's a really handy feature that we have. What's a way that we could basically have a higher chance that all of those users are connected to the same chat service instance? Well, we could also consider consistently hashing our chat service so that we have a range of instances that are connected to that are connected for a particular server. So what we could do is we could have something like Zookeeper here, and then we'll probably have just like a routing service which wraps Zookeeper. So the client, when it wants to connect to a chat service, it'll go and it'll talk to the routing service. The routing service will go talk to Zookeeper. Zookeeper will be responsible for essentially monitoring this chat service and maintaining a consistent hashing ring of the chat service instances. And what this will say is basically like this range of chat service instances is responsible for this range of servers. So if a user is interested in a particular server, then they would connect to that particular chat service instance. And so that way we can have each chat service instance is only responsible for a range of servers, and each user is only going to connect to the chat service instances within that range. And what that means is that the chat service instances is actually, because we have it consistently hashed, they don't have to subscribe to every single instance of every single chat service or of every single Kafka topic. We actually limit the number of Kafka topics that we need to consume from. And so we don't end up in this situation where we have 20 different users that are all connected to the same chat service instance. And so we have to connect to 20 different uh, Kafka topics from a single chat service instance. We're limiting that to the only so that all the users are grouped by the server that they're actually on. And so what we can do there is Zookeeper will actually pick for us based on this consistent hashing ring when the client connects to this routing service. It'll say the client will say, I want to join server 22. Zookeeper will say, okay, which one is server 22? Um, and then uh, and then essentially give us a chat service instance for the client to connect to. And then we don't need a load balancer because Zookeeper is playing that role. And then the client will just open the WebSockets connection directly with the chat service that we're interested in, and that solves the problem where the server where chat service can only listen to a subset of the servers. The client connects to a subset of chat services. Those users are more likely to be connected to the same instance or the same group of instances of chat service. And so that makes our whole process of passing messages back and forth between the different chat services a lot more efficient and a lot lower latency. So that's a solution there. I think that works pretty well. Um, So we're out of time. This is 45 minutes. I'm pretty happy with this. We covered all of our non-functional requirements. We covered our functional requirements. One thing to note is there's some trade-offs here in terms of using Zookeeper. We need to manage our consistent hashing ring a little bit more carefully. So scaling up and scaling down with chat service has to be done a little bit more carefully so that we don't disconnect a whole bunch of users at the same time. And so we do need to consider that as a trade-off of doing this, but we do win in terms of latency here by keeping a lot of those on the same host, and we actually minimize the number of connections that this needs to make for with Kafka. I think Discord in reality uses like a combination of Kafka and they do some like batching and PubSub to handle the like extremely high write throughput there. So that's something that we should consider is maybe we need to batch some of the messages together um, before we pass those messages along to chat service because this is going to be like a fire hose of messages there. And so that's something that we really need to consider carefully as we're doing that to optimize for performance as well as scale. So that's another thing that we could dive deeper into if we had more time. But all in all, I think that we did a pretty good job. One thing that we need to talk about more is sort of observability. And We did talk about, replication here. If something goes wrong, we are handling this. Lambda was horizontally scale according to our configuration. We're eventually consistent here, so all of that's good. Um, yeah, so I'm pretty happy with how this went. And Thanks for watching.